Live streaming is on.
All right, wonderful. Well, welcome back to this next installment of Transform 2022. This is a sort of festival of digital science or something like that, subsurface science and engineering. We've got a whole host of tutorials lined up for you today, or in this session, we're going to be hearing about a finite element modeling tool for geodynamics. So I'm pretty excited about that because I know very little indeed about that topic, either of those topics actually. So I'm very excited to have Agustina here, who's going to take us through that in a minute. First, I just want to mention that we got lots more content coming up this week. So check out softwareunderground.org/transform to see sort of what's going on. The chat is all happening in Slack. There's a Slack group. So if you want to take part in that, not just during the tutorial, but also afterwards and for the next weeks and months, we'll be chatting about this topic and others in softwareunderground.org/Slack. So that's completely free to sign up. You could just come and lurk. You know, you don't have to be a vocal person, but just come and find out all the cool stuff that's going on in this space. What else did I want to say? Oh, yeah. I mean, if you're watching live, don't forget you can like DVR YouTube. So you can pause, you can rewind, you can even slow it down, I think. So yeah, take advantage of that. The YouTube video will be up for the foreseeable future. So enjoy and share, please. And also subscribe to the channel if you want to get notifications of the next stuff that comes up. That's it. That's all I have to say. I'm going to hang over to Agustina Pesce, who's going to take us through this interesting tool. So over to you, Agustina, and welcome.
Hello. Let me share the screen to start with this tutorial. Great. Okay, we start so. Thanks, Matt, for the presentation, and thanks Software Underground to let me to do this tutorial today. In this opportunity, I would like to present you a geodynamic code called Mandyoc and a showcase to simulate the evolution of the divergent margins using this code. So I will explain you how to create the input file to make the simulation, how to run the model using Mandyoc, and plot some of the results. For that, I create this repository. You can find all the material here in this repository of GitHub. Let me show you. Here you can find the same notebook that I will to do today. This is more complete than the notebook that I will show you today. And here you have all the information about how to install the software and everything. So let's go back to the notebook. So, but first, let me to introduce myself and the other instructors for this tutorial. My name is Agustina Pesce from Argentina. I doing my PhD and work in applied geophysics, processing gravity and magnetic data. And recently finished my postdoctoral research where I studied subduction zones through numerical modeling using Mandyoc and contribute to development of this software. I am the main speaker today, but you can find the other instructor in the Slack channel answering your doubts. They are Victor Sacek, Jamison Assunção, and Rafael Monteiro da Silva. I would like to point out that the development of Mandyoc began some years ago by the Dr. Victor Sacek and the Instituto de Astronomía Geofísica y Ciencias Atmosféricas de la Universidad de São Paulo in Brazil. But in the last years, we dedicate to creating the documentation, the examples, and improve everything to publish this code. Now Mandyoc is open source code viable in GitHub, and and finally we have published a paper in SHOS about this code. So let me show you. Here is the repository of Mandyoc. Here you can find everything to run a simulation, like I will show you in some minutes. And you can find the documentation websites, of course, with everything that you need. So if you want to know more about this, you can visit this website and ask, of course, in Slack. So before to start, what is Mandyoc? Mandyoc is the acronyms of Mandyoc Dynamic Simulators Code, and it is designed to simulate the Stokes flow type thermo-chemical convection, taking different compositional layers into account. And it is also appropriate to simulate Earth lithospheric dynamics on geological timescale. Sorry. The code is fully parallelized using PETSc library. Different linear and non-linear rheologies can be adopted to simulate the strain and the stress pattern in the Earth crust and mantle, both in extensional or collisional tectonics scenarios. One advantage of Mandyoc is the possibility to create scenarios with velocity boundaries conditions variables in time and space, allowing the user to simulate different tectonic pools in the same model. Additionally, the current version incorporates surface process, imposing rate of erosion and sedimentation on the top of the free surface. To simulate MANtle thermo-chemical convection, Mandyoc adopts the formulation of Newtonian fluid together with the Boussinesq approximation to solve the equation of conservation of mass, momentum, and energy. These three equations that we can see here. But let me show you to this picture to summarize the step that Mandyoc takes to solve the conservation's equations and perform a simulation. This picture shows that once the codes start running and the input file are read, but Mandyoc use the effective viscosity field to calculate the velocity field and check if the convergence conditions satisfies a given value. While the minimum tolerance is not right, Mandyoc used the Usawa method to interactively calculate a new velocity and pressure fields. The updated fields modify the viscosity field, which perturbs again the velocity field. So this field will be updated until the tolerance is reached. The compositional strain history is tracked by particles present in the interior of the finite element. The exchange of particles almost in the along the subdomains of the model is efficiently parallelized using PETSc functions. The free surface of the Earth can be simulated and is numerically stabilized using the free surface stabilization algorithms. So here I will show you 3 papers that will that they use Mandyoc to solve the problems, the geodynamics problems. So in the repository you can find the links to these papers. So I hope I hope you have an idea of how Mandyoc works. I know that is a little difficult to understand in the first moment. If you want to learn more about this code, you can visit the Mandyoc website or read the paper that we published in SHOS or ask in the Slack channel, of course. So, in this moment, I am going to introduce you a particular model that can be made using Mandyoc, but in the Mandyoc repository, there are another examples to start to play with Mandyoc and making simulations. So let me show you this. If you go to the repository of Mandyoc and go to the examples example folder, there you can find another examples that you can perform as examples and play on how to make a model and make a simulation using Mandyoc. So in this tutorial, we want to simulate the evolution of divergent margins, taking into account a plastic rheology and the seam reef geodynamics. I am going to explain you how to generate the initial setup to obtain the resulting simulation that you can see in this GIF. So, there are a few ways to run this simulation. The ones that I am going to present here came from the assumption that the geometry, temperature, and velocity at the beginning of the simulations are known. Because of that, we must prove the velocity, the temperature, and the geometry of the model as input files. These input files are the interface with the boundaries between the different layers of the model, the initial temperature file with the initial temperature field, and the initial velocity file, obviously, with the initial velocity field. So the idea is to generate the input file that create this setup. You can find different layers. This is the profile of temperature that we want to generate, and the velocity. We only have velocity, horizontal velocity, in the borders of the model. And you can see, of course, the domain of the model. So first of all, to do that, we need to import some Python package. They are NumPy, Pandas, Matplotlib, and warnings only to turn off any warnings that we can generate in this notebook. And also we will import some functions in this part. This function these functions was created by me only to make this tutorial more readable. So we need to run this cell, and now we need to define the domain of this model. In this case, this model comprises 1600 by 300 kilometers squares. So we define LX equal to 1600 E3 because we want everything in meters, and LC equal to 300 E3, and enter and run the cell. Now we need to discretize this domain in element of 1 by 1 kilometers. For that, we define the number of nodes in both axes as nx equal to 1601 and xc equal to 301, and run the cell. Now we need to generate the point of the axis because we want to generate a mesh grid. For that, we want to use the NumPy line space function. So x equal to mp dot line space, and put here we want an array that goes from 0 to lx with nx values, and we generate c equal mp dot line space from minus lc to 0 with nc numbers. So now we run this, and now generate the mesh grid using the NumPy function. So now that we have the domain defined, we can generate the input files. So for this simulation, the domain is have different lithological units. These units are the asthenosphere, the MANtle the lithospheric mantle. We have here a mantle seed, a lower crust, upper crust, and the sticky air. They are our 6 different layers. The weak seed, or the mantle seed that we put there in the picture, is a small layer into the lithospheric mantle to ensure the nucleation of the rhizome at the center of the numerical model. So now, before to start to generate the interface file, we need to define the thickness of these different layers. For that, we are going to define h underscore s air equal to 40 kilometers, h underscore lower crust underscore crust equal to 20 kilometers. Oh, sorry, here I have a typo. 20 kilometers. So we need to define the thickness of the upper crust as h underscore upper underscore crust equal to 20 kilometers. And all the lithosphere will has an thickness of 130 kilometers. So h underscore litho equal to 130 kilometers. And here we define the location of the MANtle seed. This will be 30 kilometers below the lower crust, like we can see in the picture. So run the cell, and now we need to generate the interface of these layers. Believe me when I tell you that this cell creates a dictionary called interfaces, which contain the depth between the different layers using the thickness that we defined before. So here only generate that dictionary with the different layers and use the thickness to generate the depth of the different interfaces. So I will run this one, and here only in this, sorry, I have a typo. Sorry, here. I have a typo in the name of the thickness of the lithosphere. So I run again these cells. So, great. Now, in this cell that we have here, I'm only plot the different interfaces using a for loop for that, and of course matplotlib. So if we run, and everything are in kilometers, so you can find here, you can see these interfaces, the different interfaces, and the depth of the interfaces. Here in blue, we have the interface of the asthenosphere and the lithospheric mantle. In red, we have the interface between the lower crust and the lithospheric mantle. This one is the interface of the upper and lower crust. In brown, the interface between the air and the upper crust. Here in green and the yellow interface are the interface of the weak layer seed. You can see that they have the same depth because we define this in the interfaces dictionary. In this moment, we are going to create this MANtle seed that we don't have defined yet. So for that, we want that this seed will be in the center of the model. So the horizontal position will be 750 kilometers, and this seed will have a thickness of 6 kilometers. So I will run this, and here in the cell, and only use conditional statement to add this thickness to the different interface that generate the weak layer. So if I run this and plot again, use the same cell that I used before to plot the interfaces again. Now you can see that we split the interface, the seed top and seed base for the seed mantle. So we generate the interface for the mantle seed. So now we have all the interfaces created. So now we need to define the properties of these different layers to generate the interface file. Because I think that I never said that the the interface files contain the depth between the different layers and the compositional properties of these layers. Sorry. So to create the to define the properties of this layer, we are going to adopt the viscoplastic rheology where the effective viscosity combines nonlinear power law viscous rheology and a plastic Yale criterions. So the viscous component is given by this equation. So the different properties that we need to specify in the interface files are the compositional factor, the density, the rheological heat, the per-exponential scale factor, the power law component, the activation energy, and the activation volume. So in the table that you can see here, we have all the values that we are going to use for for all the interfaces. So here are the parameters, and in the vertical we have the parameters, and in the horizontal we have the names of the different layers. In addition to simulate the free surface, we adapt the stick air. We use the stick air model. So the 30 kilometer for the air layer will have a low viscosity and density similar to the asthenospheric air. Here, so taking this because of sorry. So now here in this cell we need to define define the density of the upper crust and the lower crust and generate the radiogenic heat for these two layers. Please remember these parameters because we are going to use them to generate the temperature file. So now here you can see that we only transform the table into an string called layers properties, because in this other cell that we run here, we generate an interface file called interfaces.txt that contain the properties, the layer properties here, and here we save the depth between the different interfaces. So if you go to the repository folder, you can find here the interface file. So in this file, you can see here the different properties of the layers, and here the depth, the interface depth between the layers. Here is for the asthenosphere and the lithospheric mantle. This one for, and this one, this one for the stick, for the mantle seat. This one is between the lithospheric mantle and the lower crust. This between the upper and lower crust, and here between the air and the upper crust. So now we generate the interface file. So the next step is to generate the input temperature file. For that, the initial temperature structure in the lithosphere depends, and it's 0 degrees Celsius for in the surface and 1,300 degrees Celsius at the base of the lithosphere at 130 kilometers. And the sublithospheric temperature will be the adiabatic temperature that is given by this equation. So before to define the temperature structure here in our model, we need to define some parameters. They are the thermal diffusivity, the kappa, the C capacity is the specific heat capacity, temp underscore P is the potential temperature of the mantle, G is the gravity value that we here put temp, and alpha is the volumetric expansion coefficient. So now we are defining the structure, the temperature structure. So here in this line, we are defining the a linear temperature for the asthenosphere. Sorry, for the lithospheric, for all the lithospheric. Here we are defining the adiabatic temperature. We calculate the adiabatic temperature for the asthenospheric. Here we put 0, the value of all the nodes over the into the air layer. And here we only add the temperature, adiabatic temperature in the temp in the temperature grid that we generate at first. So we add the adiabatic temperature in the nodes that are located in the asthenosphere. So now we need to apply the 1D diffusion equation in the model but before to do that, we need to create the initial heat production model, or so because of that, we need to initialize H as zeros values for all the nodes in the grid. But we change these values of 0 for HUC and HLC because we want that the nodes into the upper crust and lower crust have another values different to 0. And these values are the values that we use in the to generate the interface file. So I am in these 2 lines, I do that. I put these values into the H array. So run these cells, and now we can apply the diffusion equation for 10,000 of years using an equation that I create for this tutorial. You can, if you want to know more about this function, you can go to the tutorial repository, and there you can read about this equation, and if you have any doubt, you can ask in a Slack channel, of course. So now we apply this equation, and in this cell, I only plot the thermal structure and a thermal profile. So because I that, I use contour F, a matplotlib function to plot the temperature, and use And then I plot the temperature profile and the interface because it's more easy to see the change of temperature. So here you can see this one is the temperature for the lithospheric structure, and here we have the adiabatic lithospheric values for the asthenosphere. And this one is the temperature for all the domain, the temperature structure for all the domain. And we have for all the depth over 0 have a temperature of 0. So now we only save the structure temperature into a file called input underscore temperature underscore 0.txt in all. So if we go to open the initial temperature file here, you can, this file includes the temperature of each node starting at the bottom left of the model and going up in that direction. So here we have all the values of temperature for the nodes. So let me go back to the notebook. So now the last file that we need to create is the initial velocity file. For that, we need to, it's more easy to understand the file using this picture. You can see that we have only velocity in the borders of the model. In the rest of the nodes of the model, we don't have velocity. So in this case, the velocity field simulates the lithospheric stretching, assuming a reference frame fixed on the lithospheric plate on the left side of the model. And the plate on the right side moves rightward with a velocity of 1 centimeter per year. The velocity file in the left and right boundaries of the model is chosen to ensure the conservation of mass and is symmetrical if its adopted reference frame moves to the right with a velocity of 0.5 centimeter per year relative to the left plate. So taking this into account, I need to say that in this cell, I generate the velocity model. Here I only define some parameter. This, I will don't show you these cells with a lot of detail because they are very complicated to follow. But here I define the velocities, some parameters that we need to generate the velocities file. And here initialize the velocities like zeros for all the nodes in the domains. Here use conditional statement to generate the velocity for the left side of the model. So I change the 0 on the left side of the model for other value, only for the horizontal component. Here I do the same, but in the right side. Here I try, and in this cell I check if the conservation is the inflow the inflow on the vertical boundaries below the, no, sorry. I check here that the inflow is the same value that the outflow, only flow. So I'm only compute this. And then if we have some difference between the input and output flow, I assign this value in the vertical velocity for the node in the left side, only that here. So if you can see here, I plot these velocities for the left and right side, and you can see that we don't have velocities in the vertical component of the left and right side, but we have different velocities for the left and right side in the horizontal component. 0 for the air, 1 for. So now in this cell, and only save these velocities, this velocity structure as an input file called input underscore velocity underscore 0.txt. So now we have all the input files that we need to run this model with Mandyoc. So in this moment, I will make a stop and take 10 minutes as break, and we can continue with this in 10 minutes if you want. So let me put the clock here to take a break for 10 minutes. I will see you in 10 minutes, okay? Thanks.
Thanks, Agustina. You can maybe turn off your video and your mic and then just leave it on that. That's great.
Great.
Love it. See you soon.
Okay.
Oh,
I will. The video I. Oh, I closed the video. Sorry. Let me find the video. Yep.
perfect. See you soon. Hey, Agustina. I'll let you take it away when you're ready.
Okay.
That cuckoo
Great.
looks cool, by the way. Yeah. Thanks for using that. I haven't seen that before.
Thank you. So we can generate the input files to obtain the initial setup that I show you before in the picture. So now we can run a simulation using Mandyoc. But previous to do that, we need to create another file called parameters file. These files, there are many parameters that we need to define and take into account when we're running a geodynamic simulation. Depending of the type of simulation you want to, you need to define some of these parameters or not. Sometimes this parameter file can be a nightmare. So in this moment, I will show you this parameter file and explain some of these parameters that we need to define. I only explain these parameters because they are the more important parameters that we need to define for this simulation. In this case, in this parameter file, we need to define the number of Lagrangian particles in each element. So for that, we need to put particles per element underscore element equal to 40. Sorry. We need to specify the maximum time and step for the simulation. For that, we define these two parameters. The first one, step underscores max equal to 40, 40,000, sorry, 40,000, and time underscore max equal to 10 million years. 100 million years. We need to specify the temperatures boundary conditions. For the temperature values will be fixed on all the sides of the model during all the simulations, and the nodes for the air layer will be always 0 temperature. We need to do the same with the velocity. We need to specify the velocity boundary condition. In this case, we'll adopt free slip on the top and the bottom of the of the border of the simulation. To avoid asymmetric lateral homogeneous model, we adopt a random perturbation of the initial strain in each infinite element of the model. For that, we need to specify this variable random underscore initial underscore strain equal to 0.3. And then we need to predefine the rheology set. We need to set the predefined rheology model to use during the simulation. In this case, we select rheology underscore model equal 9 because Mandyoc have this type of rheology assigned in number 9. This is for the viscoplastic rheology that we define when we create the interface file. If you want to see more about these parameters or the other parameters that you can predefine in Mandyoc, you can go to the Mandyoc documentations. There you can find more information about it. And see the different examples that we create in the repository, because depending of the simulation, you have a different parameter file. So this big cell is generate the parameter file. You can see that we have a lot of variable here. We define the geometry, some simulations options that we need to define. Here we use the number of particles. Here the time constant, where we have define the step max and time max that we see before. Here we define the viscosity values that we are going to use in the simulation. Here is about the input and output files. You don't worry, it's easy to understand this. You can find this information in the documentation. These are, we here define some physical parameters. And here we define the boundary velocity, the velocity boundary conditions, and the temperature boundary conditions. Again, here that we see, we use the same that we explained before. And here we set up the rheology model equal to 9. In the Mandyoc documentation, you can see the other types of rheological model that you can use with Mandyoc. So if you run this cell, you generate a parameter, a file called param.txt. And if we open this file, let me find here, we have the information that you see before. Only that. So now we have everything to run the model. So to run a model, you need to run the model, you need to have Mandyoc installed on your PC. In the tutorial repository or in the Mandyoc repository, you can find all the instructions to install Mandyoc in your computers and explain there how to run a simulation. In this case, to run this model that I create, I need to open a terminal. Sorry, here I open a terminal and type. In this case, I will use a virtual machine. So I need to log into this virtual machine. Sorry, give me a moment. I forgot to put my password. So I go to the transform repository, because there I have all the files. Here we have all the input files and the parameter files. So for run the model, I need to type mpe run dash n equal to 2, because here I specify the number of CPUs that I want to use for run this model. And now I need to call Mandyoc, and we here to set up 2 flags for Mandyoc. Here we put minus seed, we put 0,2, and minus strain underscore seed, and put 0.0, comma, 1.0. So what are going to do this flag? The first flag seed specify which layer will have a specific initial strain. This layer are the numbers 0 and 2 for the asthenosphere and the mantle weak seed in the middle of the lithospheric mantle. The second flag, strain seed, specify the magnitude of the initial strain with respect to the each layer indicated in the previous flag. In this case, the asthenosphere will have no initial strain and the mantle seed will have an initial constant strain of 1. The other layers will present a random perturbation of the value of the initial strain, and the maximum magnitude of this initial strain is defined by the parameter random initial strain that we define in the parameter file. So if I press enter now, I have a typo here. Sorry, it's MPE run, not MPE run. So if I run, start Mandyoc to process the initial files first and start to solve the stock system. Then give me a minute to start. This take time is not so fast. So they start to calculate the velocity fields. So I will stop here this simulation. Sorry. I'm stop the execution of Mandyoc in these first time steps because the complete simulation can take many hours. In my case, for this model, this took me around 2 days using 8 CPU cores. The time is relative to the complexity of the particular scenario, running 40 million years in time steps in a few tenths of thousands of years. Additionally, this scenario has nearly 500,000 of nodes with 20 millions of particles tracking the composition and the other physical properties. So this is very complex. I could have chosen a simple scenario for this tutorial, more that we can to run in this tutorial, but this type of model are not so geologically interesting. Because of that, I prefer to do this model and then give you the homework to run this model in your computer when you have free time to see the output. So let me to come back to the notebook. So you can run the model in this moment, but in the repository of the tutorial, I put a folder called output. When there you can find some different files for different properties and for different time step that Mandyoc generate for these simulations in computer. So we use these files to plot the results and see the simulation and see the temporal evolution of the model. So you can see that the different files that Mandyoc generate say the density, the strain, the temperature, the time, the velocity, and the viscosity data. So to plot these file, we only need to specify, in this case, the initial step that will be 0, and the final step that will be 50, 100, and the step 100. So here I use a for loop only to go to read the files and plot them. To read the files, I use functions that I create for this tutorial. You can find them in the repository tutorial. So I only load the time, the density, here the accumulative strain, the temperature, velocities, and density file. And then use matplotlib to plot the results. For that, I use Ctrl F to plot the density with the accumulative strain. Other plot that I will generate is the temperature and the velocity using Quiver. And I also plot the viscosity using PC color mesh. So if we run this cell now, we generate 5 pictures, 5 different pictures with the in different times. This is 4 times 0 million years, here 8.5 million years, 16.9 million years, 25.4 million years, and 33 million years, and the last one is for 22 million years. So if you see we'll see the last one. In the last one, you can see that the dark and light orange color represent the upper and lower crust, while the dark and light green colors represent the lithosphere and the asthenosphere. And the shadows of the shadows of gray indicate the magnitude of the accumulative strain. Here we have the density with the accumulative strain, here the temperature with the velocities, arrows, and here the viscosity. And finally, here I generate a GIF with all these pictures, with more pictures to see the evolution. But this is the GIF that I show you to the beginning of the notebook. There you can see the evolution of the of this model. So you can see how to generate the faults in the upper and lower crust, and how to break up the lithosphere. So it is all for now. Thank you for your attention. I hope that this tutorial will be useful for you. And if you have any doubt about how to use Mandyoc or run a simulation or something, you can find us in the Slack channel or in the Mandyoc repository. So thank you.
Wonderful. Thank you very much, Agustina. That was fantastic, and I love that you started at the perfect level for me. Anyway, I hope others found the same thing. I could follow along. I love these animations. Really, really cool. Makes me wish I had a cluster or something to run those things on. But I might give one a go. So anyway, thank you to you and your team. I know there are a few people in the Slack there and others that have been involved in writing all this code. And thank you very much for open sourcing it. It makes a massive difference to the rest of us and to our community. See you all. There's another tutorial in a little while later on today, and then several more tomorrow. So hopefully if you're watching the live stuff, we'll see you soon.